So here's where we are. We're still working on understanding everything there is to know about acid-base titrations. And so far, we've gone through the calculations that you can do when you're dealing with a strong acid, strong base titration. We were using HCl and NaOH, and we did two different types of calculations. One, calculating what the molarity of an unknown, in our case we did an unknown acid from titration data, and then the other one was calculating the pH during an acid-base titration, not at the equivalence point, but some other random point. And so what we are ready to do now, so we've done everything we can do with strong acids, strong bases. What we're ready to focus on now is strong and weak titration. So either a strong acid with a weak base or a strong base with a weak acid. And these types of titrations are just a really different sort of problem. The concept is the same, but we have to take a few things other things into consideration. So let's consider what we're going to use for our example is a strong base plus a weak acid. Now, I do want to tell you that if we're doing it the other way around, so a strong acid, weak base, it's going to be the same types of issues, and we're going to use the same type of problem-solving strategy. And we will do examples of strong acid, weak base titration. So the problem that we have with a strong base and weak acid titration has to do with the pH during the titration and also at the equivalence point. Let me see where we can find it. When we're doing a strong acid, strong base titration, one of the things that we definitely know with a strong acid, strong base titration, at the equivalence point, the pH of our solution is going to be 7, because with a strong acid and a strong base, the products of a strong acid, strong base titration are neutral. And so we can rely on that, and it does help to make the calculations quite a bit more simple. With a strong base, weak acid titration, like let's consider our strong base NaOH, and for a weak acid, let's use CH3COOH. That's a good weak acid. And when these two react together, the products of this reaction are NaCH3COO, no minus sign, and H2O. And so this is our base. So it has a high pH. And this is our acid. So it has a low pH. And water, we know, is neutral, so that means that it has a pH of 7. This ionic compound right here is the sodium ion, which is a neutral cation, and the acetate anion, CH3COO-, that's a basic anion. So this is also a base, which means that it has a high pH. And the formation of a base in the strong base weak acid titration is one of the things that complicates these types of calculations. Because when we form that sodium acetate, NaCH3COO-, I keep wanting to say minus. Let's just get rid of the cation because I clearly don't want it there. That CH3COO-, that basic anion that we form, can react with water in equilibrium, and it can remake some of our acid from the titration. So it's going to put some of it back, which is going to complicate things. And it also makes hydroxide, which is how it contributes to the high pH. So what I have made for you to help you navigate through these types of calculations, I've made you this worksheet that it has a series of steps of what you need to do when you are dealing with a weak and strong titration. So this could be for a weak acid with a strong base or a weak base with a strong acid. And on this worksheet, the first type of problem that we're going to solve is an equivalence point calculation. So that means that we're being asked, what is the pH at the equivalence point? We're going to also do weak, strong calculations at some other time, not at the equivalence point. Those are two separate types of calculations. So when you come across these problems on ALEX or other places, what I want you to do is go back to this worksheet and follow these steps. So step one, the first thing that we're going to do, if my dog is sitting with me and just constantly licking my hand, so if you hear a weird licking noise, it's my dog. I hope that you don't hear a weird licking noise. So step one for this, first thing that we're going to do, write an equation for the reaction between the acid and the base, whatever it is, the strong acid or the weak acid, and the strong base or the weak base. And you've practiced this a lot, so you should feel comfortable writing a reaction between an acid and a base. Because we have a strong base, hydroxide, it's a forward reaction. It's not in equilibrium. The base is going to take one of the hydrogens from the acid, and that's going to turn it into CH3COO- acetate, and our other product is water. And then we're going to set up the framework for an ice table. So that's step one. Step two, calculate the initial moles of our acid. So we're going to do that using the volume and the molarity of the acid. And actually, if we're making this generic so that it applies to anything, we're going to calculate the initial moles of whichever molecule we have both the molarity and the volume. So for one of them, it might be the acid, it might be the base, one of them we're going to have both the molarity and the volume, and for that one, whatever it is, we're going to calculate how many moles we have using the molarity, 1.5 moles per liter, times the volume, 0.245 liters. And that is going to be 1.5 times 0.245, 0.3675 moles. And we're going to fill that in, the ice table, 0.3675. Remember that in titrations and with buffers, the ice tables that we build are being built in units of moles, not molarity. So that's our first thing. At the equivalence point, and this is an equivalence point calculation, at the equivalence point, the moles of the acid are always equal to the moles of the base, all the time. So if we know one of them, we automatically know the other, and we have no products yet at the beginning of the titration. So we're done with step two. Step three, because OH minus is a strong base, or if we were doing this with a strong acid and a weak base, if one of them is strong, the reaction will go to completion. All of the reactants will be consumed. Use this information to fill in the C row. So everything, we're getting rid of everything. It's going to completion. And you've done enough ice tables now to understand the concept of minus X, plus X, plus X, like that. And now we're going to finish the E row. So when this is done, we're going to have no more reactants. We will only have products. And like I said at the beginning of this video, this product, the CH3COO-, it's basic, and it will, it's a basic anion, so it will react with water in equilibrium. That's what we have to think about next. Now we are going to write an equation for the reaction between that anion, the basic anion, and water. If we're making this generic here, we're going to be writing an equation for the reaction between either an acidic cation or a basic anion that was produced by the reaction. This is an equilibrium reaction, so let's write our products out for that. The base, CH3COO- turns into CH3COOH, and we make hydroxide, and we're going to set up the framework for an ice table. Now we're going to get ready to fill in the ice table. Step 5, calculate the total volume of the solution. So what we're trying to do here is set up an ice table that's going to be in molarity instead of in moles. So our total volume of the solution is going to be the volume of NaOH plus the volume of acetic acid, CH3COOH. Let's see what we actually know from the problem. Up here in the problem, the volume of the acetic acid is 245 milliliters. What we don't know is the volume of the sodium hydroxide. It gave us the molarity of the sodium hydroxide, but it did not give us the volume of sodium hydroxide. However, we figured out in this first part, we figured out that we had 0.03675 moles of hydroxide. We know that that's how much we reacted. And the molarity of the sodium hydroxide gives us the relationship between moles and volume. So we can use molarity like a conversion factor to go between moles and volume. The molarity is 0.8, which means that we have 0.8 moles in every 1 liter. So we know that we have 0.0459 liters of NaOH. That's a lot. 45.9 milliliters. So our total volume is the volume of the NaOH, 45.9, plus the acetic acid, 290.9 milliliters, or 0.2909 liters. Now that we know the volume, we can calculate the molarity of the CH3COO-. So we're on to step 6. We're going to use the moles of acetate from the ice table and the total volume of the solution. So the moles of acetate are 0.3675. And the volume in liters is 0.2909. So that is 1.2 0.6 molar. I'm hesitating right now because I'm trying to double check my math. I want to just double check my math and make sure that I have not messed anything up. I'm looking over, I'm like I'm recalculating these moles and the first ice table up here, making sure that those are correct. That calculation is correct. The total volume calculation, we know this one is correct because that was given to us in the problem. Oh, here it is. I was gonna say, I thought that I made a mistake somewhere. I did. I see what I did. When I got here, you see that I added that extra 0. We've got to deal with that. 0.3675. So we have 0.459 liters, which means that we have 459 milliliters, which changes our total volume a lot. It felt like something was wrong. 704 milliliters. Okay, so that means we've got to fix this molarity calculation. 0.3675 moles divided by 0.704 liters. Our molarity is 0.521. Much better. Okay. So we've calculated the molarity of the acetate. We've calculated the molarity of the CH3COO- at the end of this particular point in the titration. And that is going to be what we start with when the acetate starts reacting with the water that's present in the solution. So we're going to make another ice table. Before the acetate starts reacting with water, we don't have any CH3COO- or CH3COOH, because see up here in the ice table, we got rid of all of it. And we also don't have any hydroxide because we got rid of all that as well. So these are zeros. And this is now a standard weak base equilibrium pH calculation. So we're ready to fill in the initial rule. We did that on the second ice table. Now fill in the change with x's because we don't know to what extent this is going to react. And then fill in the end, 0.521 minus x, and we are going to go back to the assumption that x is really small, so it's just 0.521. And now this feels familiar. Like now, okay, we're at a part where we know what's going on. We're going to write a Kb expression because this is a base, because it's producing OH minus. And the Kb expression, to do this, I'm looking at this equation right here. CH3COOH times OH minus over the reactant CH3COO minus. We need to, step number 9 is where we're at, convert Ka to Kb and solve for x. So let's go find our Ka. Our Ka in the problem width at the top is 1.8 times 10 to the minus 5. I'm going to copy that down here. Ka is 1.8 times 10 to the minus 5. pKa is the negative log of the Ka, which is 4.74. So pKb is 14 minus the pKa, 9.26, and Kb is 10 to the negative pKb, which is 10 to the negative 9.26, which is 5.56 times 10 to the minus 10. Now we can plug that into our equilibrium expression, 5.56 times 10 to the negative 10. We can fill in from our last ice table the stuff that we have from the ending of that ice table. Our products are both x, so that's going to be an x squared divided by 0.521 for the reactant. And now we can solve for x. X is 1.7 times 10 to the minus 5. X, look back up at the ice table, X is OH, so we can use X to calculate the POH. POH is the negative log of OH. For this problem, it's the negative log of X. It's the negative log of 1.7 times 10 to the minus 5, which is 4.77. And the pH plus POH equals 14. So our pH is 9.23.